Hello there, welcome to episode 65 of Codebase Alpha, and today's another shader stream, and we're going to be trying to do some terrain today, so a bit of a different approach from the stuff we've been doing in the last three streams. Mårten's with me again, so let's go straight over to the pair programming stream, and Mårten can introduce himself.
Yeah, hello there.
Hi, Mårten.
I don't know, I've been on the stream a few times now, and we've been talking shaders a lot, I think, right?
Yes, absolutely. So here's the shader we did last time. So
yeah, I think it turned out quite well actually.
I'm fascinated by it. I keep sitting here watching it, and the reflection of the cube as the sphere kind of rotates around, especially as you're coming up now, to see the cube inside, reflected so perfectly is wonderful.
Yeah. I agree. It's you kind of just sit there watching it and see. Yeah, and one thing I noticed as well, going on this kind of rambling notices, is that I started to observe reality differently when doing these things, because I've been thinking, when I see things in real life, I've been thinking, how does this thing work? How can I sort of make this look like this using a shader? And I live near water, right? So I've been observing water all summer, trying to see how waves and how sort of the sky reflects in a different part of water depending on the angle. So I think that's I actually like that, as well as the side effect that I actually observe reality more intense. I don't know if that makes sense. Than otherwise I just kind of sort of it's just there. But when I've been doing this shader programming, I actually sort of been more aware of things, and like, oh, this is an interesting rock. How could I do this rock in a shader? And these kind of questions. So that's a nice thing. Maybe I was actually thinking about this. So we talked about doing terrain, but what we could do maybe is, because this is just if you want to, we could try to sort of make this geometry, tweak that a little bit if you want to.
We could start off with that, yeah.
Yeah. So I think it's better to use the Kodelife tool for that. So if you bring up Kodelife, my favorite IDE. I'm not sponsored by those guys, but I want to be. So but
yeah, it's great. It's a great idea. It's great for playing around and testing this stuff. And when you've got it looking good, it's very simple to transfer it over to ShaderToy. So I think I did that just before, while I was eating my breakfast, just about to go to work. I transferred this over to ShaderToy. So
what we do is I think we picked the ShaderToy example. No, we don't. Anyway, but as you say, it's like the syntax they have in ShaderToy is a slightly more stupid version of the OpenGL or GLSL. But it's not a big problem, because as you probably notice, it's just like if the function requires a float, you have to put in 1.0 instead of 1. It cannot do that, and that's mostly what you spend time doing. And oops, sorry about that. Or you don't see. I pressed the wrong app on my machine.
No, I didn't see you do that.
That's fun sounds now. Oh boy. Oh well. So have I showed you? I think there are two sites. Have I showed you this site? I think this is a very good site for ShaderToy Pro. I think I shared it in here before. I think it's worth sharing again.
Okay.
I'm just trying to find the screen. There we go. Do you see it?
Yeah, I got it. I'll just post it over here and post it into chat.
So one thing we can do, just to sort of, if just to start simple and start tinkering a little bit what we did last time. If you scroll down here, so this contains many sort of clever sort of functions. And if you see this op union round, if you scroll down a little bit, you can do different kinds of. This is kind of different soft function. So we could actually try to use this op union stairs, or we can take the op union column function and we can use that instead of a soft mean to get a different look. That's what to try, I think, if you want to.
Give it a go.
So if you find that function, I would just search for it.
So it's op union columns, yeah?
Yeah.
Because I've got edge up here and I'm not sure how to search. Find on page. There we are. Op union columns. So that.
Yeah, union columns. Yeah. So you search. We want to find the definition.
Okie doke.
Not chamfer. Not that. Not that. Not that.
There's the stairs.
Columns is the thing we're looking for.
Okay, we've gone back.
If you type in op union color, columns, yeah, and then you go next.
There it is.
Yeah, so copy paste this whole thing into Shader Toy. I think that should just work.
Put it straight into here, yeah.
Yeah, like around the soft mean function.
Yeah. The after soft min.
And you can pause the graphics, so maybe where we can see the sphere, and if you stop the timer, because then it's easy to observe. There is a good point. Yeah, whatever. Okay, it's use R45. We need that function. So if you search for PR45, that's just a rotation 45 degrees. So you need that from that page. Yeah, if you stop that shader as well, it's probably a good idea. The function was there. You actually had it there. There it is. Yeah. So this page has, these are kind of hackers that do a lot of stuff, and they have sort of shared useful functions that they use for when they're doing stuff. And then we need pmod1, which is actually extremely useful. This is this op union columns that you use that occasionally, but pmod1, that's a brilliant function.
Okay, let's find that. Here it is.
This is used for what's called sometimes domain repetition, and domain repetition is a way to sort of do cool stuff for free, infinite. So now we have union columns. I don't know exactly what but so float A, float B, Rn. Okay, so I think if you go down to the soft mean function, copy paste this op union column, because I'm going to forget that name. No, not just the name. 4 arguments. I think I'm going to match. Be able to do it.
So soft min.
You use it in a distance function. That's up.
Yeah. There it is. There.
Yeah. So comment is out. Yes, and then you go float D equals op union columns S1 S2. Yeah.
Falling apart again. There we go. It's gonna be the same values, is it? You think?
No, not exactly the same. S1 S2, and then say 2 and 4. I'm just guessing now.
I'm guessing it's good. This is what we do, isn't it?
Yeah, and what happens there? Unexpected. Okay, let's run this and see what something happened. I'm not sure what happened.
I think we need to zoom out a bit, so let's go to the
we can do that in
camera.
Yeah. It looks weird.
It does look weird. So
that's always a good thing, I think.
Here, I think we can pull out, can't we?
Camera, you multiply by 3 instead of 1.
Oh, that's right. Yes. There we go.
But it looks weird.
It certainly does. How fascinating.
Yeah. That's also, as I always talk about, that things happens. It doesn't. It not always like you wanted, but something happened, and yeah, okay, weird. Let's reduce the numbers a little bit. Because that's the problem here.
Yeah.
Because I was just guessing these numbers. I just took a sort of out of thin air. Here, so instead of 2, maybe 0.2. And now we can observe, see what happens. Now you see what happens here is there is a different look to it. You see when it gets closer here, you see it sort of get multiple. It's hard to see because it goes in the back here, right? But what happens is there are multiple, instead of just a single smoothing, there are like multiple columns. That's what's called, right? So when you get closer, you get more. So if you pause it here, for instance, here, so here, that's good. Yeah, now we can experiment a little bit here. So if you change the 0.2 to 0.1, you see the steps get smaller. If you go 0.3, the steps get bigger. And if you instead of 4, say 8. No, 3, but 4, you change it to 8.
Oh,
then you get more steps, right?
Yeah.
So let's run this thing, see what happens. So it's a pretty cool function, I think.
I like it. Yeah, certainly gives it a different feel.
Yeah, I mean, you look at it and you're like, I'm not sure I prefer this, but I mean, it's different, and it's very hard. Yeah, once again, I talk about this being in this model of triangles. Like, if I was in this triangle mode, where I would think how that worked, my mind would have been broken.
Well, you couldn't even consider how to do it, could you?
Yeah, and here we just use the function that just give a different distance.
Interesting the way it gets close. You get the it kind of reaches out, doesn't it, with those columns?
But so what I was thinking is we can sort of make this object a little bit more interesting by using this pmod function and doing subtraction, because I think that's usually a quite way to make interesting shapes.
Mm-hmm.
So if you stop this, pause it, you save this thing, so we can destroy this logic, right?
I can save it, yeah.
Because then we're gonna mess around.
There we go. It's saved as Codebase Alpha 5.
Yeah. So what I'm thinking, we're going to keep the box, but we're going to repeat the spheres. So what I would do is I would actually where is this box on? So
box is here.
Yeah. So I would remove line 104 and 102, and yeah, you can comment it out. That's fine. And also 101. And let's see if I can go full screen on this, make it easy for me to sort of follow. No? Oh well. I'm sure I can do it somehow, but I don't know. So now remove this. So what is S1 there? Okay, make S1 equal to the sphere. So S1 is max something, just remove the max function here.
Okay.
Yeah, and remove this there.
Yeah.
And then you make float D is the max function of these two. So what happens with that? S0 and S1. No, S0, S1.
Okay.
Okay, so what happened now is you had a box and you have a sphere, and now you took the intersection between. So if you type max, it will look different. No, mean, sorry.
Yes, this is Boolean algebra with shapes. So yeah, so now we have the union of the two.
Yeah, which is cool. But what I want to do is I want to repeat the sphere infinite amount of times and then subtract the repetition from the box to create some interesting shapes.
Okay.
The way we do that is we use max function instead of mean here, because otherwise it's going to be very weird. So you above float S1, which is line 100, you type vec3 pp or whatever. This is just a backup of that position, and equal p. And now what you want to do is you're going to use this p mod 1 function, and that's quite what that function does is that it repeats the object, you can say, in one direction.
Right.
So the way you use it is, I think if I remember correctly, is you type like this, a new line, p mod 1, I think p capital M d1 parenthesis p dot x and type in 1.0. No, pp is what we should use. Otherwise, it's going to be very weird. There we go. And now you use pp on the sphere, st sphere on line 103.
Yeah. Oh, okay, yeah.
Yeah. So let's reduce the size of the sphere to say 0.2. Not there. And you make the repetition, instead of taking 1, make it 0.4 or something like that.
Oh yes, okay.
So what you see now, it's actually repeated itself in x dimension, and this is actually an infinite repetition. But the reason you don't see it infinite is because we limited by the box. Because we have this box. Yeah. So if you would remove this box, you could just say d equal s1, for instance. And at the next line, just type d equal s1. So 107.
Yeah, got it.
Line after that, d equals s1.
Yeah. So infinite number of reflective spheres.
But and that's okay if you do it in x dimension. But if we're going to do it in all dimensions, and then will not see anything. So the box is good there to sort of help us sort of do that.
Yeah.
So what we can do now is we can actually repeat it. If you copy paste that same line there, and you do it for the y-axis, and you type ep.y.
Oh, okay, yeah.
And then you do it for the z-axis as well.
Okay, look at that.
Yeah, so that's pretty cool, right?
Spheres, yeah.
Yeah. So now we have actually repeated this object a few times. What you also can do is you can change from 0.2 to 0.4 to 0.5 in one of the dimensions to sort of change how it's repeated. Like so. I think we actually might go for 0.5, right? For all of them. Let's just try that.
It's like a crystal lattice now, isn't it?
Sorry?
It's like a crystal lattice.
Yes, it's become kind of a crystal lattice here, right? Which is cool, and the reflections work, by the way.
They do. It's fantastic in the bottom there, yeah.
Yeah. So let's type minus S1 now instead of on line 109. Yeah. So that looks a little bit boring, but what we're going to do now is going to reduce the size of the box. So if you reduce the size of the box here up here on 0.7 to 0.5, 0.7.
Oh, yes.
So what we've done now is that we have created a box here and we subtracted. Let's zoom in a little bit and see how it looks. (0.1 perhaps. 1, I mean.
Yeah. Sorry. Yes, it's
maybe rotate it a little bit so we can get a feeling for how the object looks. So if you start playing again.
I'll just make it 1.5, I think, so we can see it. Let's play it.
Yeah.
It's like a piece of machined metal, isn't it?
Yeah. Yeah, and because of the reflection in the spheres, it becomes this kind of thing. But what we did. Hello, the Dragon's Eye, by the way.
Oh, Dragon Eye, hello. Welcome.
So what we did here is and this is a very, I think, how you construct how you can construct objects that look non-trivial, but using trivial operations, if you see what I mean.
Absolutely, yeah.
And because what we did here is something very simple. We have created a box, and we have a sphere function, but using this domain repetition function that allows us to sort of repeat the sphere infinite amount of time in different directions, we get a different kind of object, and then we subtract that object from the box, and we get something that looks. I mean, it's not. You can certainly see it's being repeated, but it's hard to imagine once again if I was in this triangle world, like how the heck would you do this thing?
Yeah.
So let's tweak the numbers a little bit to see if it changes in pleasing ways.
Okay.
That's what I do. I tweak numbers and I see, oh, okay, this was good. I keep this. So maybe 0.4 instead of 0.5 on the box size on line at 9.
Yeah.
Less
interesting.
0.6. Yeah. Interesting. Now you can sort of see the curl. Let's make the sphere a little bit bigger. Let's make the sphere 0.25, perhaps. Maybe that's 2.2, line 105. Add a 2 after the 0.2.
Okay, yeah.
So maybe even more. 4, perhaps. 2.4. Yeah. Yeah, this is okay too. So you know, it's very simple to sort of experiment, I think, with this domain repetition and create interesting objects, in my opinion.
Yes.
On this thing here, right? So that's something I want to. I just want to, before we get started on the terrain here, right? We sort of bring this up, that this pmod function is brilliant in that it allows us to sort of repeat an object a number of times, and then we can use Boolean algebra, but for shapes, to create non-trivial shapes using trivial operations.
Yeah, yeah, it does. I think you could play around with this for ages to
That's what I do.
Sculpt that out. Yes.
Yeah. Let's just, for fun, before we move on, remove line 103. How does that look? Comment it out. Okay, well, that's pretty cool as well, right?
Yeah.
I think. You know, we have a sphere, and then you have sort of subtracted this thing from the sphere, and we have the reflections going and all these kind of things. And of course, I think it's also it's also quite cool if you just repeat that thing here. Take that back, that line.
Yeah.
Sorry, I said the wrong word here. And if you remove this minus S1, and you just have the plus. This is also an interesting object.
Yes,
I think
this is very interesting. Yeah.
Yeah, and you look at the reflection. You can see this
inside
reflections
there, all the reflections inside. Yeah.
Bouncing around, because that's what the ray is doing when we send in the ray here, that it bounces around a few times, and we can also see its reflection. So it's looking pretty good, I think, actually. When we look at the stream, I have better quality there. Yeah, look at all those spheres on the sides.
Yeah.
Cool stuff. Did we do that last time? I think we did. So the endless possibilities to sort of waste hours on sort of.
Yes, that's one of the things that's kind of problematic with it. Is you can literally sit here and just kind of. I've sat in Shader Toy just changing numbers by fractions of.
And see what happens. Like if you have these, especially if you have these fractals where you tweak a number a little bit, and this looks very interesting. And then often what I do is I add like a sign factor that depends on the time, so to sort of make it change by the time, and then you find something interesting and you keep that thing here. Maybe I have something I could share. I don't want to distract us too much from the sort of the main thing, but where do I have that? I think give me a second.
Okay, no problem. So welcome everyone to the stream. Good to see everyone in the in chat. So just say hello in chat. Dragon, I thank you for joining. So we're just kind of doing a bit of preamble before we start looking at terrain generation. So we're gonna start off quite basic with that one and just try and build it up to something which is half decent, so we can give you an idea of how how you'd go about making terrain with shaders. It's a different kind of concept from the distance functions we've been doing.
But it's not. It's kind of
similar, isn't it? Yeah, related.
Yeah. Let's stop this thing right now. I'm looking for. There is something else I like to do. I like to sort of do spherical transformations and then back to rectangular. I think we did that once.
Yes.
And that allows us to do weird stuff. And weird stuff is always good. So I'm going to share some functions here. I think they should just work. Let me see if I can find the thing here. Oh, here it is. So I share it in the.
Yeah. So this is the changing of the coordinate system, isn't it?
Yeah. And I found I like changing the coordinate system because what you can do is you change the coordinate system and then you tweak the coordinates a little bit and then you go back to the normal coordinate system and you see what happened. So what I would suggest we do now, just for fun of it, is if you go down into this, is that here, right?
Distance estimating,
yeah. I don't know before or after. It's always hard for me to tell. Let's say before. PP off line 113.
Yeah.
After that, you make WEC3. Let's call it RP. I don't know. I don't know. Something. PPP. It doesn't matter.
RP
can
be fine.
Yeah. To what is called? To spherical.
Let's get it from here. So it was too spherical, yeah.
So we transformed the coordinate system into a spherical coordinate system, PP.
Oops.
And then we immediately say PP equals 2 rectangular. RP. And if you've done that correctly, now you spelled wrong here, but
yeah. No, I didn't want to break with tradition.
I know, exactly. Now nothing happens because because we didn't change anything really.
Yeah, well that was the idea, wasn't it? We change it back again so we can make sure nothing bad happens.
Yeah, but let's see if we can tweak. If you take the RP here. The RP coordinate before and we change it back, right? Just a new line. So you go RP dot set y plus 1, something like that. Let's see what happens. Plus equals 1. I mean.
Ooh.
Yeah. So weird stuff happened. So to say. And that's always a good thing, weird stuff. We like weird stuff. So what we can do now is we can take. Okay, so that was interesting. So instead type sine, instead of 1, you type sine, sine, I time. So we change it according to the time value. Okay, so what the heck is this? I don't know, but it looks funny, right? So we transformed it to the spherical coordinate system, and then we adjusted one of the angles by the time factor. We just added to it, and that sort of transforms the space of this thing here.
No, what happens if we do that to the y-axis as well? See, I'm getting into this.
Yeah.
Not quite as interesting.
No, the y-axis is certainly the most interesting thing. But I mean, weird stuff happens. Remove the. And the x-axis, that is the radius. So we could try to modify that as well. See what happens.
Just change it y to x, or do you want to?
Yeah, that's right.
Yeah.
I mean, it's not going to break.
Oh, I like that. It's a shame it turns into a box.
Yeah, it seems like this is mostly zooming.
Yeah.
But let's try. Can I type something?
Yes.
This makes no sense at all. This has no meaning. But it could be, like that. What the heck is this? So what we did now is we suggest the radius depending where we are in the, and now we see we get distortions, but it doesn't matter. We had some fun doing it. We take the x coordinate here, and then we change the radius of the system. You see here it's weird. So when you distort the space in this way, it kind of makes it hard, but it still looks like something.
Yeah, it's very strange.
Yeah, it's weird stuff. So you can see how you can waste stuff here, but I kind of liked it. I kind of like this sign.
Yeah, I like that one as well. Yeah,
I think that looked kind of neat. So let's change it back to sign, I think. Yeah, you have to type. I cannot type here. That's weird, and weird is always good. And like I said, reflections and everything, they work, right?
Yeah, absolutely. Everything's working really nicely, and I like the fact it doesn't go into a complete box. So.
Yeah. So that we can spend the whole stream looking at this thing, I think. But shall we try to? But I just want to sort of talk a little bit about domain repetition and kind of domain sort of distortion using these coordinate systems. There are millions of ways of doing this, right? Really, and to create kind of interesting shapes and often what's nice. I said this many times on this stream. Something happens, and sometimes it just looks rubbish, and sometimes it looks kind of cool.
Well, it's just experiment, and as you say, 9 times out of 10, it's not that much good. But you can just kind of tweak it around and see what happens. I mean, we could try multiplying this by a constant and see what happened there, couldn't we? Anything we want, really.
Yeah, that's right. I mean, as long as we don't write loops, infinite loops, it's not going to crash. It's just going to look weird. Yeah, 0.1, what happens? Yeah, so then the distortion
is lessened.
Yeah, exactly right. So what one can do then is like you start with small distortion and sort of increase the distortion and so on and so forth. It's like, yeah, let's multiply by that by 6 approximately. That's almost like. Yeah, I'm not sure what I'm looking at.
No, it's very hard to understand what that is.
It doesn't matter. Shall we start talking about terrain shaders?
Yeah,
they are an interesting domain as well.
I think I'm going to save it at that point there, and we can.
Yeah, save it.
Yeah,
keep it. Ship it.
We'll definitely keep it. We'll ship it up to GitHub, and people can play with it and see what they can see if they can get something. Maybe we'll have a competition for the weirdest possible distortion that people can do with that shape.
Yeah, I mean, but it was see how simple this was. We just added this spherical coordinate system. We tweaked a little bit in the spherical coordinate was a room, and then we mapped it back, and something happened. Okay, maybe the other kind of mappings we can do. Maybe we can map it using the Möbius transform, and then tweak it in the Möbius transform, map it back, and it can look rubbish or it can look awesome. I don't know.
And that's the fun, isn't it? Not knowing.
There are millions of sort of transformation between coordinate systems, and that can give those cool graphics. And the spherical one is just a very simple, conceptually simple. There are many others, as you know.
Yeah.
I don't know what happy we do with the Fourier transform. I'm not sure that's going to work out, but maybe.
Okay, so we'll start a new file then, shall we? And,
yeah.
Okay. So
from the scratch.
Yeah, from scratch. I'll just save this. So we've got a place to put the code. Base alpha 6. As if you do want to get this code, then it's all up on GitHub. You do need the Kodelife IDE in order to open the KL proj files, because they are actually binary files of some kind. But it's a free IDE. Go to hexler.net. I'll just type that into chat. That's where you can get Kodelife, and you can have a play with those files.
Okay, so It's free IDE, but they have a little bit of nag screen saying, well, if you like this thing, you might want to buy it, but you don't have to. Okay, let's stop the coloring thing. So a terrain shader, as mentioned, it works a little bit different. Well, I'm sure there are many different ways of doing it, but the ways I've been doing it, and you remember we looked at a quite interesting terrain shader last time that was just a few lines of code.
Yes, it's 7 lines of code, I think it was, wasn't it?
Yeah, and it still looked pretty good. And the way terrain shaders work is that instead of having a distance function telling us the distance to an object, we have a height function telling us the height of the terrain above some level, right?
Right.
The sea level, but you know. So instead of defining a distance function, we're going to define a function that represents the height of the world, so to say.
Okay.
And I'm going to suggest we're just going to make a simple sine function.
Okay.
So let's try to build this from scratch a little bit. And so what you do is you make a function that returns a float, which is a height, and then you call it height function. Now, a difference here between the other functions we have, then we put in a 3-dimensional coordinate, but here we're going to put in a 2-dimensional coordinate because we're going to navigate through a 2-dimensional plane and we get the height for that thing. So that's the difference. So
okay.
We put in P here, for instance.
Okay.
And then for the fun of it, we just return the height function can just be return sine, the sine function, and p.x.
Okay.
So this height function is just it will just be a sine wave across the x dimension.
Yes.
If that makes sense. So we're done there for the moment. Now we also need a way to sort of compute the normal of the plane, and I'm just going to give you that function.
Okay.
And then we can talk about it. But it's basically like the other normal function when we talk about distance functions, but it's slightly different. And the reason is that we don't have a distance field, but we have a height field kind of instead.
Okay. Yeah.
So, but I think it should just be possible to add that depending on how we made it. It has to be below height function because it uses height function.
Keep forgetting that we've got to have it in the right order.
Yeah, this is like F#.
Yeah.
I think you can make at least like in C you can declare a function ahead of it and then you can use it.
Okay.
So what this thing is, we have an epsilon, which is a small value.
Okay, epsilon. Okay, yeah.
Yeah, and then we have a height function, and then we subtract the epsilon here, and we produce the height value by modifying the x-axis and the y-axis, and then we have the y-axis here that becomes that is just the epsilon value because that is because of the height factor. How this is to create this kind of field, so like a distance field, and then does the same thing as Alex. So it's not very interesting. It's just the same thing, kind of. Yeah. But because this is not a distance function, it works slightly different. But then we normalize it, and then we get a vector that points in the direction of the normal of the height field.
So in normalizing, we're just bringing it back into a range of plus or minus 1, are we?
The length is 1. That was normalized.
Yeah.
But the normal function, as we talked about before, is very important in order to get the colors right. Like because the normal function determines kind of the what should I say, the brightness of the pixels, or like it's like a basics. If without the normal we can't do anything, so we need that. But now we have it. Now what we're going to do now is we're going to write. I'm also going to give you this function because so we get some progress.
Okay.
but instead we talk about this function because they are not magical in any sense. So I share that, I think, with you. So this is the Raymarsh function.
Yeah.
Okay, we need some constants here, right? Mean distance, max distance. I define them. I will give them to you. And then we talk about this function a little bit here.
So this is very similar to the Raymarsh we had last time, isn't it?
Yes, it's if you've seen Raymarsh, this is nothing strange really. It's kind of a dumbed down version almost of it. So now compatible. So, but this thing works a little bit different, and the reason it works different is if you go to the top of this function, we have the ray origin, that is where I is, and then we have the ray direction. This is where we travel, and then we also, for reasons that we're going to get later, we also give back how many times we iterated to get the result. And then what we do is we start at we compute a vec p, which is the position we're currently at, and then we ask what is the height of the terrain at the xz axis.
Yeah. So rather than what's the distance to the remaining, what's the height? Yes. Okay.
Yeah. And then we check, have we gone past the distance? We could actually move the check earlier, but okay, if the distance is longer than if the distance is longer than max distance, we're just going to return max e3 equals to I and just return.
Yeah.
Otherwise, what we do is we compute the height difference between where the I is and the height of the plane.
Yeah.
Or not the I, where the ray currently is. Sorry.
How far the ray has marched so far, yeah.
Yes. And if this thing has gone below the sort of the terrain, then we have an intersection. That is what this says.
Yes.
We've gone below the terrain. Now we have an intersection. And then we just return the distance we travel.
Yeah.
That is what we're doing. Otherwise, we travel a little bit. And with the distance function, we always travel, how far is it to the object? And then we travel that distance, right? It's very simple.
Yeah.
With the height, we use the height as an approximation. So if we were high above the terrain, what we do is that we travel that distance to sort of try to find the intersection. So if we are 100 meters up, we go 100 meters and we try to find something. And this will not work for more complex terrains because then we're going to overshoot the top of the mountains.
Yeah.
But we start simple, right?
Yes.
And then we make this more complex in order to sort of fight at artifacts. So I could give you a much more complex function, but that's much harder to understand, right?
Yeah, we need to start simple.
Yeah. And it's going to work, I think, pretty fine with your sine waves because sine waves are very smooth. So they're going to look all right, I think. This thing here is just to sort of, the further we travel, the faster we travel forward because the further we get away, we don't need the same precision as we need when we're close.
Yeah.
So this is just to improve the performance of the ray marcher so that we travel further to find an intersection faster. Because if you're far away, it doesn't really matter if you miss the ground by a few meters or whatever.
Yeah, quite.
And that's kind of it, really. This is how the ray marcher work, but it's slightly different than with ray marching. But the reason this works differently is because the ray marcher don't really work that well. Because when we cannot really answer the question of the distance to the. What we have is a height function. We don't have a distance. We need to use the height function. So that is why we need to change this thing a little bit. But we're getting there now. So what we should do now is I think we should start writing the get color function to compute a color. But we can take something which we always use when we use this, and that is these are exactly the same as before, and they are the functions that compute the ray and the ray origin. So I shared them with you in this.
Where would you like these?
I want them at the bottom.
Okay. So we just need to tidy up this. That's time. I think that's just resolution.
Oh, I see. I used a different template here as well, right? So you want to use the main function here, right? Or the main function, perhaps you can call the main image. Yeah, that's probably a good idea. Okay, let's do that like that. Yeah.
Night times living in somewhere.
Yeah. And
High time there, yeah.
so if the main function call the main image function, the get color doesn't exist yet. We're going to define that.
Okay.
But I think it's correct if what you do is you call main image with UV as a coordinate. I don't know, sure no. Can I type a little bit?
Yeah, sure, yeah.
Yeah, because I use the shaded toy template to do this.
Yeah,
right?
the resolution bit might need to be tweaked as well.
I can't copy paste.
We'll
I wanted to copy paste it. Let me try it again. This is the usual thing here, very hard for me to do. Copy.
Can't understand why that doesn't work for you, but who can tell?
I don't know. I can't accept it.
Okay.
There we go. Paste, right?
There it is.
I think this is actually correct here. UV, except we need to compensate UV for the resolution.
Yeah.
Whereas I think it's correctly computed. Might eat those words. And then we're just going to remove this thing here.
Yeah, I think I'd also need to adjust my resolution, actually. I'll do that in a minute.
Yeah, do that.
So I think it was 1920 by 1080.
Rambling Geek. We come
Hey,
in at a good point.
Rambling Geek.
We are currently rambling. Oh, sorry.
I'll just change this and then yours. There we go.
Need to navigate more with the mouse than the keyboard.
So Rambling Geek, my bot welcome to Live Coder team members has just worked. Copy Birdie, welcome as well. And it's yours is working well as well, so that's good. Now everyone's got one. So
what we do now is we write this function, which is called the get color function, and you can remove the main image function now. I think.
Will do, yeah.
That's not.
I was going to ask about that.
So now what you do is we define this get color function. Yeah, this is a good idea. To always save because it's so easy to sort of write a loop and then you just crash out.
Yeah.
So and get color is defined above get sample. Vec3 get color, Vec3 RO, which is array origin, the I position.
Yeah.
And Vec3 RD, which is
the right direction. Yeah.
Direction, and then you there, and this should produce colors. If you return Vec3 1, I guess the background screens should be white.
Yeah.
Yeah. So that's a little bit bright. Let's go for 0.1 instead.
That's better.
Yeah. So what do we do here? So we have this ray marching function, and the goal of get color is to do the ray marching, and using the result of ray marching, we want to determine if
we're intersected with the terrain, yeah.
So the first thing we can do here is to sort of see if we hit the ground or we hit the sky.
Okay.
So what you do now is, if you remember, you can type float h. H is the height of float d. Sorry, float d, which is the distance the intersection.
Yeah.
And then you call the march function. I think it was the name, right? March.
March, yeah.
RO, RD, and max iterations. You can type. I call it max. No, not like that. It's an out parameter.
Okay.
So max underscore iterations or something like that.
Okay.
And then you go, and then you need to declare this thing. The max iter, you need to declare it before the march function.
Is it float, is it?
No, it's an int. So what happens now is if d that is returned is less than the max distance, we hit the ground. But if it's max distance, it's hit the sky.
Yeah.
So let's just return two different things depending on whether we hit the sky or hit the ground.
Okay, so this is sounding very familiar.
So if d is less than max distance, that means we hit the ground.
It's max underscore distance, was it?
I believe that is so. I don't remember. My memory is very bad.
We'll find out in a minute.
I think we are a perfect combination. My memory is awful, and your typing is, well...
It's awful. Let's not beat around the bush.
Don't take it bad. So together we form a dream team. And then you return for the sky. You return you return maybe blue for the sky and green for the ground, something like that.
I don't know what those would be.
0, 1, 0. 0,1. That's a weird color.
Yeah. I'll get there in a second.
There you go. 0.
Yeah.
Look at that.
We've already started to see it, yeah.
You see something. And then you return black or whatever. But to be honest, we see the shape now of the sine waves, right?
We do, yes. So we have some rolling hills.
Yeah, some rolling hills. But they're obviously not very interesting. So we want to improve these rolling hills. And you can also remove the last return. So the reason now we come to this normal thing, right? The reason it's uninteresting is we want sort of the hills to be colored differently depending on what the normal is, because the normal determines the normal determines
it's the reflection, isn't it, of light, really?
The reflection and the diffuse lighting.
Yeah.
Together with the light. But in order to have the light, then we need to add the light. And then I would suggest that we add some kind of skybox or some sky.
Yeah.
And I have one prepared, which I hope is good
enough. Just like Blue Peter, eh? Here's one you did earlier.
So let me...
So I'm going to get Vector to announce live code as well. That'd be really cool. I love Vector. Okay, looks good.
Yeah, I'm going to remove this ambient. We don't need it yet. But here I define...
what I'll do is I'll get the constants in first. I'm into logical location.
Oof.
I know. Let's try and program, shall we? Some constants up the front.
That's not what we do when we do shaders. In shaders we just put code.
Whack it in.
Yeah, whack it in. See what happens.
Okay, so we got the sun direction and a sky color, so they sound like they go together.
Yeah, and the sky color you put above the get color function.
Okay.
And you see we have a sun direction here. That's a very useful function, because the sun direction here we will use that thing to to compute the direction towards the light. Oh, okay. Now we need the rotation function as well. I have that prepared as well. It's very easy to write this. We've written it last time.
We see. These are apart from the sun direction, these are quite familiar.
Yeah. So the rotation function is like this. What this function does is that it rotates. It rotates a vector a certain amount of degrees. So it takes a position and then rotates it with an angle. This is a very common operation. You do it all the times.
Yeah.
And now I think it compiles. So what we do now, instead of for the sky here, instead of returning 0, you return get sky color.
Yeah.
Oh, there, exactly right. Sorry, I'm looking at the wrong screen. Yeah, here, right.
Yeah.
My fault.
Oops.
I have the American spelling, I guess.
Yeah.
What do we need? Yeah, you need the ray direction.
Oh, it's not get sky, it's just sky color.
Sky color RD. Oh yeah.
There we go. There's the sun and there's the sky.
Yeah, so there's a sun in the sky there.
High
fidelity sky. The ground is not so high fidelity yet, but we're going to get there. But we talked about how the sky works, but we can talk about it quickly again if people missed it last time. It's a very simple idea. So we have the sun direction that we ask from there, and then we take the dot product between the ray direction where we're looking and where the sun is in the sky in the direction. And what happens if this direction we're looking at is the same direction as the sun? That is the most intense spot. But then we want to have a kind of an aura, like the
corona, isn't it? Yeah.
Yeah, corona, right? So I'm not. Yeah, okay. So in order to do that, what we do then, we take the sun dot and we power it by 30 and to 60 to get the difference. If you comment out these lines, these two lines here, so this will remove the big corona, and this will remove the kind of the sun spot, because they have different intensity there, right? And you add them back, and you can tweak on this power level. Like at 600, you can change it to maybe 100, and that will give it a greater spread.
Yeah.
So you can tweak on these things to get different sort of looks of these things here. The angle thing is to create a sky that is toned. So so you get kind of when you look up further, you have a different color than when you're looking along the horizon. I was just chancing this together. I mean, putting random colors. I thought, it's good enough.
You just threw it together, just on the way to the stream.
Yeah, but you can certainly sit and tweak on these colors to get some pretty nice looking skyboxes.
Yeah.
And it's also possible to add Perlin noise and all these kind of things to create clouds if you want to do that. But we're not going to do it this time. We can do it another time. So let's try to sort of create some shading on our sine waves. So now what we have, in order to do that, we need to compute the normal, right?
Yeah.
And we had a function for that allows us to get the normal.
We do. That's the get normal, I think it was called. Get normal, yeah. Do we do it here?
Yeah. No. Keep that thing, or keep. Do it like that. That's fine. No. Okay, but that's that. Yeah. So you make a new function called bec3 normal or something like that.
Do you want to do it here, or do you want to do it outside this loop, outside this if statement?
No, inside it.
Okay.
Because we don't need it outside.
Okay.
Get equal get normal, and then you pass in what is the position, right? Oh yeah, you have to compute the position where we're at, and that's very easy to do. So you say, go down there. You say vec3p. You make a new vec. No. Sorry,
yeah.
I'm not clear.
I'm with you.
We need it many times.
Yeah.
I don't think this helps so much. This IntelliSense or whatever. I turn it off. But you go vec3p equals r. So where are we now? We are on the surface of the sine wave.
Yep.
So we go RO, ray origin, plus the distance traveled times d times RD.
Okay.
And this is what you pass into this. Now, it seems like I forgot this thing here. Sorry. Oh yeah, the normal function also just takes the 2D coordinate. So what you do is you type p.xz to sort of select the xz coordinates, and then you type comma d, because this reduces the precision of the normal the further it travels.
Yeah.
Because it actually looks better when the normal has less precision, because otherwise you had an abnormal amount of details in the distance, and that looks weird.
Yeah.
So what you do now is you compute the diffuse lighting between the light and take the diffuse lighting for this point, and the way you do it is to just take the dot product of the normal.
A vector, is it?
No, it's the dot product turns a scalar, a float.
Okay, so float.
And then you take the dot product of the normal and the sun direction. What did I call it?
Sunday, I think it was. If we've got access to Sunday, we haven't got access to Sunday at this point.
Yeah, but you can save that as a variable.
Sun direction, yeah.
We probably need it for more stuff. No, make a variable for it.
Make a variable, yeah.
It's not unlikely that we actually need it for more things later on.
Okay.
So, and then this can turn negative. We don't want that. So what you do is you say you take the max for this thing, max dot 0. Yeah, comma 0.
Yeah.
Or you put the 0 somewhere. Like that. So now this will never go. What you can do now you can return vec3. Hopefully I've done this right. I'm guessing now. So it's always scary. Vec3 parenthesis DL.
Ooh.
Yeah. So what you see now is, at least we see the shape right now, because we added the diffuse lighting to it. So that's a step forward, because before we couldn't see the shape of the sine waves.
Yeah.
Shall we make this a more interesting world?
I think so. It's very uniform.
Yeah, it's very uniform. Let's save this. So we don't mess it up.
Yeah, we're all saved.
So so now if you go to a height function, what you can do now in this height function is that you rotate the p function, the p value before we. So what I would do, I would, instead of just returning this sine wave, I would introduce a variable f, a float height.
Wow, look at me.
C
sharp programming today.
Yeah. We don't need that here in this fancy stuff like that. And you have to remove the return as well.
Oops. Yeah. Okay.
And then you go return f. And now let's just rotate the world here, because it's a little bit, it helps us see the object. So what you do is you type, before this you type a new line, type root, R-O-T, pass in the p vector, and rotate by angle of 1, for example. Now this is radians, right? So,
yeah. Okay, yes, we've certainly rotated it there.
Yeah, so -1, perhaps? Better? Yeah. The problem is the shadows are very deep.
Yeah.
Yeah. Yeah, well, we will fix that. Minus or plus 0.5 perhaps.
Yep.
I think minus was better.
Yeah.
Okay, but how do we make this more interesting? And one way to make this more interesting is we rotate again so what you do is you take this thing here and you copy paste the rotation line and add it below float F. And then we rotate again. And then what you do is you add the sine function. You take F plus, instead of float F, you take F plus equal. No, not like that. Underline. What we're going to do is we're going to superposition sine waves on sine waves.
Okay. Okay, yes, it's starting to distort into some hills and valleys. Very deep shadow at the moment.
Yeah, we're going to fix that, but we can sort of see it. But the thing here is, this is not going to look completely right. So what we're going to do at the same time, I borrowed the mouse cursor here, is that we're going to oh boy,
scale it a bit. Yeah, I'll do that bit. Look at that, yeah.
And we also increase the period. By that.
That's a bit too regular.
Yeah, but the thing is, what we can do now here is we copy paste this again.
Right.
Hard this.
Ooh.
Yeah, now it got weird here.
Yes, it's been very interesting.
Yeah, I think the normal looks like it's messed up. But what we do here is that we are sort of yeah, it's hard to tell. What we do here is that we are superpositioning now a smaller wave on top. So we rotate the world and we increase the frequency of the wave and we superposition it on the big wave.
Mm-hmm.
And that is essentially how these terrain generators works. When we do these things, is that we are continuously sort of, you know, I cannot get the plus sign.
Okay, I can talk about that. What if we rotate it by slightly less?
Yeah, can sort of make it there. So what I want to get across here is a little bit that we can we start with something that's very regular, but then we add the same regular function again, but we sort of, you know, increase the frequency by double frequency, but also reduce the amplitude to half of it.
Yes. And
this is the technique almost everybody uses when they're generating terrains, which is a very simple technique. I think you can agree.
It's just a couple of sine functions, yeah.
Yeah, but I think what we can do is we can improve this thing here to sort of make it look better, because one of the problems now is we cannot really see. One of the things I think, can I borrow the mouse cursor?
Yeah, yes.
Yes. Can you put the semicolon here?
Yeah.
I'm gonna put one here and multiply by 0.5. So that looks better.
So just flattening a bit. So yeah.
Yeah, because it was too intense, right? So now it looks more like a desert.
Yeah, it does. Yes.
Yeah.
Desert at night.
Yeah, and using extremely simple techniques, right? The only thing we did here was that we took a sine wave, we rotated the position, added the same sine wave, but we've increased the frequency and decreased the amplitude, and then rotate again. And that's a very simple process. And what we can do now is we can actually rewrite this as a loop. I think we should do that.
Okay.
So what you do now is you, instead of you can say float f equals 0, and then we write everything as a loop. And we can keep the initial rotation, because we might want to have an initial rotation before we start. So
let's comment that. I mean, shader toy mode, then writing the float for the for loop.
I don't really know. I mean, floats are cheap these days, but I just don't like comparing floats.
Yeah, well, you can't do it accurately, can you? So.
Yeah, it's maybe it depends on the number, and that's never a good thing. So if now we have to save. Because it's so easy to mess this up. You remember last time?
I do, yes.
Yeah. Because what happens if you write an infinite loop, shaders tend to crash. But I think the best thing you can do, you make sure that the code doesn't, just put in a line above so it doesn't compile. So we can complete like X here. Just put a line. So this, make sure no, that might compile.
That won't.
This doesn't compile. And then you type int I equals 0. I less than 1. Plus I. Yeah, whatever. And then you there. Yes. But what now you need to introduce a couple of variables as well here. And what you're going to introduce is the variable, a scale variable, which is the amplitude scale. No, what do we call it? Let's call it amplitude. No, outside the loop. So float amplitude, or whatever you want to call it. Yeah, and then you go float period, which is period here. Period.
Okay.
Not period at all.
That's absolute classic, that, isn't it?
There we go.
I do speak English and can spell English as well eventually.
The
Dragon Eye says he's animated his avatar in Scilab. That would be interesting to see on the terrain. Post it in Discord. Thank you, Dragon Eye. We'll have a look at that.
And now you can remove the X, I think. Here.
I think we're safe there, do you? Should we sort this?
I think it's okay. We just have a single loop here. So what you're going to do is, instead of f equals, float f equals, you're going to do f plus equal here.
Yeah.
And then you're going to multiply the sine wave by the amplitude. And the position, the period here, the period as well. And below here, yes, that's correct. Then you remove the other plus equal. And what you do now here, remove it, correct? You multiply amplitude by 0.5 to scale down each iteration. And you multiply the period by 2. And this is the numbers we can tweak and see how it becomes. And now I think you can remove the X. Yeah. So it's very, but now you can, if you save it, now you can change the loop from 1 to 2.
Yeah.
3, 4. Yeah. not so, the list looks.
It starts to get looking a bit odd, doesn't it, after a while? But yeah.
Yeah, but I think around 3 it
one's
looked
okay.
like
Yeah.
quite decent desert actually, right?
Yeah.
Let's start the amplitude at 0.5, and then we can remove the last multiplication. And you remove multiply by 0.25 there, right? Yeah, maybe the amplitude start at 0.25, right?
Yeah.
Something like that. Okay, but now we have a desert here, right? Shall we improve the lighting or the shadows?
Yeah, it's very monochrome at the moment. Yeah.
Yeah, but we can see that the shape it's like a terrain now with a desert. Do you agree?
I do. Yes.
Yeah.
It's beautiful sand dunes, actually.
Sorry?
It's got beautiful sand dunes.
Yeah, it's not. I mean, considering. I mean, once again, I think this is simple. I don't know what you think, but this is what we added some sine waves, and it looks like a desert. That's amazing to me.
Yeah.
And using the same technique, we can actually make this look like mountain ranges. And very, I think, realistic looking, although probably not realistic in real life. But we can make them look good.
Certainly good enough for computer games, things like that, isn't it? So where things are very exaggerated and colourful.
And this is all real time, of course. So this is just happening when we look at it. So let's look at how we can improve the what's called the shadows and all this kind of, because we want shadows and we want better light, we want better effects here. So let's go back to the get color function. I'm gonna think a little bit here. So let's improve the color. I was experimenting a little bit with colors before. I thought this turn was a quite good color for sand dunes.
Okay.
So let's try that one.
Where do you want that color?
Just add it inside this function, get color function, somewhere. So you make a const vec3 sand color under the D. Yeah, somewhere in here.
Okay.
I'm going to switch back to your screen here. And now sand color. Instead, you multiply DL by a sand color.
Okay, right. Oh, yes.
So it has more brownish tune to it, but it's also very dark. So we will make it sort of not as dark in the. Let's see now, so I'm thinking a little bit here.
It's okay. You carry on.
So oh yeah. So usually how we do it is it gets too dark to sort of go here. So I'm going to write something here.
Okay.
So what this does is that it just improves. It makes the dark parts less dark.
Right. Oh yes. Okay.
Yeah, maybe that was a little bit too non-dark, but a little too intense. Yeah, maybe that's not.
Yeah,
that's a start, right?
Surface of Mars now, right?
Yeah. And another thing we want to do is, and this is a thing we often do, is that we want to sort of make it sort of fade out in the distance.
Yeah.
And I'm just going to share a function with you here. It's not very complicated. No, actually we can write it. So the way we do it, we use the mix function again. So you make a call. Instead of return, type vec3 call. equal, and then you take return call. And what we do in order to make it sort of fade out is we say that the call now is equal, and we're going to use the mix function here.
Okay.
Which is a very good function. And then we're going to start from call. Oh yeah. Call, comma, sky color. So this is a good. So now what you do is you take the sky color down here and save that in the variable up here, because we're going to use it in multiple places. So sky call. So yeah.
So that's a vec3, is it?
Yeah, vec3 sky call.
Okay.
And then you use the sky call down there as well.
Well, I misspelled color again, have I? Yeah, I have.
At line 156. 156. We can type 0 after sky call, and it should compile.
Okay.
So at line 156, you use sky call as well. Here.
Yeah, I got it.
And you remove the parentheses. So it's just unnecessary to compute it twice. So if you change the 0 at line 150 now to 1, it completely disappears.
Yeah.
So the mix function, what it does is that it what the mix function does is that it if you take 0 to 5, you get the
half and half. Yeah.
Yeah. So now if you take 1 minus d divided by max distance, so d is the distance you traveled. Let's see what happens here. So that was not the intention. So let's remove the 1 minus then, because it kind of faded out now.
There we go. It's got misty in the distance.
Yeah. I mean, that's
pretty cool.
I already think it looks a little bit better with the mistiness, right? Don't you think? It adds some kind of realism to it, don't you think?
It does. Yes.
Try to play here, because I think we go forward. If you press play on the control.
Oh yes, we are moving forward. Yes.
So now we are flying over our sand dunes.
So this is the helicopter drone which is going to fly over the surface of Mars in a couple of years' time.
So what we're lacking here are shadows.
Yeah.
And one of the things lacking. So let's add shadows. Now shadows aren't complicated to implement, but it's a short implement. So I'm just gonna once again share this with you, if that's okay.
Yes, Dragon Eye says small changes make powerful effects. Yeah, and that's part of the fun of the whole thing, really. Just,
yeah. Like because before we added this, that it turned out it looked kind of artificial, but now yes, it's still artificial, but it's still for me more appealing. If you see what I mean.
It's softened everything, and the fact it does fade out is what it would do in reality, isn't it?
Yeah. So I shared a function here with you. So this is a shadow function. It produces the shadow. And so so for people that haven't looked at this, we can just talk about this loop and figure out how it works. It's a very simple loop here. So we find a get shadow function.
Yeah.
So what this function does is that we start from the point where we are. Now, in order to sort of save time here, we start at the point where we intersected the plane.
That's right. Yeah.
Or the mountain ranges or the sand dune, and then we have the array direction. So the naming here are not perfect, but we're going to walk towards the light. That's what you hear. You shouldn't walk towards the light, but we're going to walk towards the light here. And
good poltergeist reference there.
Yeah, and float LL is the maximum distance we're going to walk toward light, because we're going to give up after after a while, because the distance is like, the light is infinite far away. So we're just going to walk some part of distance. The mean is the minimum step, and the k, I don't think even the k parameter is used. We can try to remove that thing. Comma, remove comma.
Yep, there we are.
And so what this thing does is that it steps 24 times. So we start and we ask the height function, are we below the height? And if we are below the height, then we have intersected it and then we return 0.
Right, yeah.
If we at some point have gone beyond the maximum length here, we kind of say, well, then we return 1. So 0 means we are in shade, 1 means we are not in shade.
Mm-hmm.
This is very sharp shadows. And then we step at least 0.1, but also the higher we get, the higher increase the step. So it's the only thing this tries to do is try to see if the ray towards the light intersects the terrain.
Yeah.
Because if it does, we should be in shade. So let's call this function inside the getColor function. So we have the sun direction. We're going to walk towards that, right?
Yeah.
And we have this position P. So let's make a float. Now we have to do it inside.
In the loop,
inside. Yeah. So let's do it under DL on the line 161. And then you call shadow or whatever you want to call it. I use equal shadow. What's the function called shadow? I don't remember. Immediately forgot the name.
It was called shadow, yeah.
And then you pass in the position P. This is where not RO. Position P. The sun direction. And what was it? Was it? I forgot.
We want RD. RO, RD. I mean, it's got LL.
I said the 4 or whatever. I think 4. Just pick a number. 4 is good enough. We tweak on that. And the mean T, what should that be? I need to consult my example. This is just one of the parameters you experiment with. 0.1.
Okay.
So now we have the shadow, and now we're going to use the shadow effect to sort of see. And the way it's very simple. What we're going to do. The only thing, now we have the shadow. It's 1 if you are in shadow, and it's 0 if it's 1 0 if you are in shadow, and 1 if you're not in shadow. So just you multiply col inside the mix here, inside the mix function. You multiply the col by the shadow.
Okay,
yeah, plus it's not correct. You want to multiply.
Multiply, yeah.
It looked cool though.
It did, yeah. Wow, look at that.
We have shadows. Let's move. Let's start the timer. See and walk here.
Yeah, but the shadows are moving with us.
Yeah, so we have some issues with the corners here, right?
Yeah.
But I mean, we can see that there are shadows, and it can be. These are like things we can tweak on and sort of make sure that they look better. For some reason, it's a little bit imprecise here. Maybe if you change 0.1 to 0.01 or whatever. Yeah, that was the wrong direction. 0.2. Yeah.
Starting to settle down, isn't it?
Yeah. Okay, well, this looks a little bit better, right? Yeah, but I mean, we can tweak this. I still think the shadows looks a little bit too sharp.
They're too dark, aren't they? Yes, they need to be a bit more diffuse.
Yeah, I agree. They look too dark. But you know, that is what happens. Oh yeah. Yes. Okay. Yeah, that's how I did it. I mean, I need to consult my old examples again because I'm like, but you know, we have the shadow. That's a good first step. Let's compute the shadow above here. So you move this thing above above the DL. Yeah, so this is a little bit cheating. And then I use shadow instead of 1.0. I think, no, wait, how are we going to do this? I have to think a little bit. Sorry.
No problem. You think away.
Yeah.
So Dragon Eye is saying there's less atmosphere on Mars, so shadows may look like that. You never know.
But this is not certain. This is Mars either, right?
So it could be Alf's home planet, you know.
Yeah.
She got an Alf Commando on the bot.
Let me try something.
Yeah, you go ahead.
I will just tweak a little bit here, see what happens. So I try to think what it should be, and then I'm like, I cannot come up with what it should be. Then I just tweak on it until it works. That's my usual strategy.
That sounds like my approach to programming. you write the simplest thing that could possibly work, and then tweak it till it's good.
Yeah. Okay. No, this looks good. So I need to think a little bit here, right? So DL, what we do is we multiply this by. I'm going to change this code a little bit here.
Yeah.
Okay, this looks interesting already.
It does, yes.
And then we go float. I don't know. Try common grade. I'm not sure this is correct. Equal sign, please.
Sorry. There you go.
Mix 02. Dot 0 shadow multiplied by DL. Yeah, doesn't this look a little bit better?
It does.
Because we have shadows now. We see that here. We see that this is in shadow, right? But it's not as dark as before, or like more like this.
Not quite stark, is it?
Yeah. So this is an improvement, don't you think?
Yeah, I think it needs to be slightly lighter. Maybe not quite so dark as shadow, but.
No, I did something wrong here. Well, that probably explains why it didn't look exactly right.
Okay.
Yeah, okay, well. Experimenting a little bit here again. 02, 03. This isn't really.
It's quite sensitive, isn't it, to the values?
This is once again, experiment. What is this? What is this?
Looks a bit like.
Now it's very abstract, right? But now we see this is the pure shadows. What we see here. Sorry, where undo button? Okay, can we leave this for now, and we can keep it for now, I think, if that's okay by you, and we can sort of tweak this and go back here and think about it a little, because I want to sort of change this a little bit and sort of work with the shape.
That's looking good.
I mean, it's a start, and also when I do this, sometimes I got stuck here. Let's drop that for a moment and move on. What we can do here is we can also try to move the sun here and see if the shadows.
They do, yes.
So what we can do, what I always do, is this thing. I thought I did.
That's what I time, yeah.
It is a little bit too intense, the shadow. I agree.
Yeah.
But we fix that later. I think right?
Yeah.
It's something we can experiment with. Is this okay? Keep it for now?
Yep, I'll save that.
Yep. So now let's increase the number of iterations we have on
Right at the top then.
the height function and see if we can get something interesting. So we can go back to 1 here, right? Then we get these sine waves. They're kind of boring. Then we get there, a little bit more interesting. Yeah, the shadows are just too dark.
Yeah.
They look like big blobs.
Like pools of ink, aren't they?
Yeah. I don't really understand why they should be so dark. I have a hard time dropping that because they're too dark.
Is it because that we've got this 1 and 0? Is it?
Yeah, we must, but maybe. Let me think a little bit here again. Yeah, this is usual. Thinking on stream. That's a hard.
I know thinking, speaking, and coding is very, very difficult. All on stream. Yeah, you just need the time to just sit back and look at it, and then or walk away. It's what I tend to do when I get a problem like that.
What we could do is just this thing here. Let's try that and see if that helps. Go up here. I feel like let's say we don't just return. No, that didn't. Nothing changed.
No, it's not that obviously.
This time? It's not used or what? Am I confused? So confused. Shadow is this.
That's it there.
Maybe it's
getting confused. Yeah, it took it to shad. Yeah.
No. Here we have a problem. We double multiplied it.
Yeah, right.
Now we're getting somewhere.
Yeah.
Because we did all this work, hard work, to sort of make it look better, and then we just throw that hard work away by multiplying by shadow at the end. Where was this function again here? The shadow function?
There it is.
Yeah. Okay. Now now it looks less like this
a lot better
gigantic blobs, right?
Yeah.
It still might be a little bit too much. Now this is okay. I think it's okay.
I think it's looking good.
Yeah. Let's go up here and tweak this thing here, right? Oh yeah. I need to look at the stream how it looks. Yeah. I mean, I think it's slightly better. I mean, this is not really what you want, but we can change. This looks pretty good, I think.
I think it's good with 3 or 4, yeah.
Yeah. So let's try to make a mountain range instead.
That sounds good to me.
Because what we've done now is that we just have sort of, use sine waves. But how can we make mountains? And this is where noise comes into the picture.
Okay.
So let's copy paste this function here.
The height function.
Yes. Because we're going to keep this one, right? So and then we.
Oops. Oh. There. I want to do that. It was a comment this one out.
Yeah, so you call one of them underscore or 2 or whatever, something like that. Like so. So now I'm going to introduce it to a very cool function here. We'll see what happens. Click shade stage here. I thought I clicked stage.
Sorry, I was doing something. Yeah.
Yeah. So we're going to add a texture here. Is it texture 0? No, here? No. Is it previous pass? I'm looking for texture 0, but I'm a little confused here. Sampler, previous pass. But we don't have that. We have a texture 1.
Mm-hmm.
Oh, texture 0 it says. Okay, good. Yeah. So, oh yeah. I think I'm gonna start by removing all of them. And then we're going to add, how do you do that again? I forgot that. How do you do that? Parameters perhaps? Built in. Noise.
Uh-huh.
Do you remember what is it? Sampler 0 that was called? Sampler 0? Is that our variable?
Can't remember.
Yeah, I immediately forget. Texture 0.
Texture 0, yeah.
And we can make it 512 times 512. And now it says white noise. White noise is not good for mountain ranges. We can try a Perlin noise instead.
Okay.
Which is often used for mountain range. I used a different one, but Perlin should be good. So what we want to do now, instead of sampling the sine function, we want to sample this texture and see the height function for the texture. So that is how I'm going to rewrite this function here. So let's just take this thing here, see if I can successfully do this here. Texture, no.
So okay, somehow you're typing over on the. I'll let go. You carry on.
Texture. Is it texture 0? Is that what we said?
Yep. Just need to change the name of height function.
Yeah, I know. Yeah, now we just have to figure out why we don't see anything. Okay, I don't know what that happened there. This is a little bit of experimentation here, right? No, P is, what is P? It's vec2, yeah. Period 2. Yeah, I don't remember what this had to be here. Make it look, but the idea here is that instead we try to sample this texture.
The texture, yeah.
Is correct. No, but it looks like we don't have much details here. Okay, that was weird. 3. If everything falls apart, I might need to copy paste some code.
But that's fine. Let's just copy paste the code.
Yeah. But the idea is this, right? We have a texture which contains random noise, and then we try to sort of, can you give a multiplication sign? We try to sample that text as a height. Multiplication sign.
What do you want the height there?
No, sorry, I pressed the wrong button. I should press it. The period. That didn't help. I'm going to need to review an example.
Okay.
To get this right. Give me a second. But you get the point, right? I think what the intention is here. That instead of using a sine wave, we are using a text. We're using a
random texture. Yeah. Yes. I've just put into chat the we've got on our bot, we've got an ask command which you can ask any question. So I've just put in what is Perlin noise. So if you're wondering what Perlin noise is, a definition there.
I wonder if you bound the texture wrongly. It does look, yeah, or maybe it's maybe we try this thing here. So I'm just gonna try some things because we have to find the scale correctly for this thing here. This is hard. as usual.
Multiplication. There you go.
Back to P scale. Set the position. Yeah, so the issue is we have to find the correct scale of the texture, or hopefully we are sampling the correct texture, because it says sample right here, right?
Yeah, texture 0.
Yeah, so I was kind of hoping that this was the right one. Maybe the frequency is too high. No, it's very hard. Something happened.
Yeah, something happened then.
Irritating. So, but if something happened, that would mean that this is actually, yeah. So it seems at least that it's, you know, it's sampling the right. It's sampling the right.
Texture,
yeah. But we're doing something wrong, or if I'm being correct, I'm doing something wrong here. So I have to sort of.
No, we take joint responsibility on the stream. We take joint responsibility. I'll probably type something wrong somewhere at some point.
Yeah. I mean, so this is, you know, a bit irritating. Once again, thinking on the stream is hard as well.
We're taking the .x here.
I'm going to clear things up here a little bit here, and so remove all this fancy logic here, and we're just going to go back to basics.
Always a good idea.
Plot f equals texture. Is that the right function as well? Texture.
Seems okay.
Texture 0. P.x.
Oh, there we go. Something happened.
Okay, it looks weird. But that's always a good thing, right?
Yeah, that's what we find, isn't it?
So we're going to remove the clamp and add repeat. No. That was the wrong here. Clamp. Where is the texture?
It's down the bottom here, I think. This one here. Noise.
I can't. Okay. Can you drag it down? I cannot drag it down.
There you go. So here they are. They're right at the bottom there now.
Yeah. So you change the clamp to the repeat.
Yeah.
Okay, so that looks strange, but it's a huge difference, because now we see something, and I think we can fix that. Let's stop the time.
Where's the time over here?
It's on the product.
Okay. Good. So we can certainly see the noise there.
This is very noisy, and it's too noisy. But to make it less noise, but there are structures. So what we're going to do here is we're going to. Can you give me multiplication sign?
Oh, sorry.
Yeah. Equals.
I'll give it an okay. Ooh, okay.
Now we see something.
Yeah.
What we're seeing now is we're moving through the texture, so to say. It looks a bit strange.
So this is the texture interpreter as a height function now.
Yeah. There are weird stuff going on here that sort of make them sort of, you know, behave a little bit different, weird here, right? But we are essentially looking at the texture, and the reason it looks weird is because when we're stepping through this thing here, we have a too trivial stepping function. But we see the shape of the texture here, which is interesting. Then I also know by experience that it's also good to add. Can I have a plus sign?
Yeah. There you go.
Something like that. Okay, that's something. So now what we're going to do is we are going to do the same thing as we did before.
Okay.
We start with float 0 here. And we're going to say f plus li equals. So we also, if you go back to the shader stage here, right? What we're also going to do is we're going to do a change. Can you scroll to the bottom?
Yeah.
And what you do is you change from nearest to linear.
Oh, okay, yeah.
So now it looks. Now, before it looked very sort of, mechanical, kind of cool in some sense. But now it looks more like it potentially could be something, right?
Yeah, could be, yeah.
Yeah. But what we're going to do now is we're going to do the same thing as we did before. Copy. Paste.
Ooh.
Yeah. And we add the rotation here. So we add a rotation P there, but we also multiply, as you know.
I'll do it. There we go.
Multiply by.
Oh, amazing. Look at this. It's starting to build up straight away.
Yeah, it starts to look like something. So let's save it, and let's implement this as a loop. So you do the same thing we did before here, right?
Yeah.
But you write a loop. So copy paste the amplitude. I don't know why it didn't work before. It didn't work. Let's forget about that.
It is.
Yeah.
Yeah.
Change amplitude to 1 in this case. Okay, now we're doing a loop. It's always a good idea to make the code not compile. We learned that.
Yeah, we certainly did. Having to write the whole thing. I wouldn't fancy writing all this again, I must admit.
Nah, it's boring. Not double int. But what we can do later on when we get this to work is we can experiment with different noise as well. Because what's cool about this tool is that you can choose between different noise, different kind of noise, and see what mountain range, what noise gives us the best looking mountain range. And you keep F and you multiply, you remove this thing here, this you don't need anymore, the last one. But then you multiply the texture here by amplitude on line 59. Up there.
I know, got it. Don't worry, I'm on it.
Okay. And you multiply the period with the position.
Okay.
And now you remove the X.
Yeah, now we hold our breath.
Yeah. Save. And change to 2. Change to 3. 4.
Here comes the mountains.
But
that's great, isn't it?
This
we can go too far, but yeah, I think 7 looks about almost.
It's probably the best one, right? Yeah. But but let's think about that again, right? What did we do here really? We took a Perlin noise texture and we sampled that. Then we rotated the position and we reduced the amplitude but increased the period of this Perlin noise, and did it again. And we did it 7 times. And for some reason we get something that looks like a mountain range.
Yeah, which is completely counterintuitive, isn't it?
how can I was kind of like thinking, how can something this simple give something that looks decent?
Do you think there's some kind of natural law involved?
Yeah.
Yeah, it would
So
seem so, wouldn't it?
let's experiment with the Perlin noise. Let's try the different noises and see how it looks, just for fun of it. So we have this type Perlin.
So yeah, I guess Sir Dragonite, we could use it in the game. Some kind
Yeah, sure. It's possible to do a game with this. I'm not sure exactly what kind of game, but
flight simulator
take the
V1.0. Yeah.
take the value noise. I don't know exactly what the value noise is, but it is top one. So that looks okay as well, I think.
It's
right?
good. Yeah.
Now we see a little bit interesting artifact, so we should probably raise the camera, or let's start amplitude and make the amplitude 0.7 or something like that. So the mountain ranges get a little bit lower.
Yeah.
Not as dramatic.
No, it's quite dramatic before. Yeah.
Yeah. What you can do is take 1 instead, because it gets more dramatic, and then you subtract f at the line 63 by 0.3. So you just lower it. That should work, right?
What do you want to subtract what from it?
0.3. No,
Oops.
not like that. 0.3.
Oh yeah. Deep shadows again.
Yeah, but we can. I don't think it's. Yeah, they are deep, but the mountain ranges are, they're coming. So I mean, let's change the noise here to value fractal. See what happens then.
Oh, yeah.
Yeah, well, this looks like a flatter mountain. Still kind of realistic looking.
Yeah.
I think. Take another one. Just for fun. See what happens. Parallel fractal. I don't really know how this noise, but interesting to see that different noise. I mean, when I thought about noise, is that noise is like, yeah, whatever, it's not important, but it has huge difference. And if you take the simplex noise, that doesn't look that good. Yeah, it's just, and I think the worst one is if you go white noise.
Yeah.
Yeah, so this looks no good, not good at all. And the guy that made the Perlin noise, he did the Perlin noise because he thought there was no good noise generators to sort of generate noise that he could use for mountains and like natural looking things, and that's quite obvious when you see this thing, I think. Shall we go back to the Perlin noise? You think about that?
Yep.
Okay, what's the next step here, do you think?
Well, do we want to try and have some snow on the tops and some greenery in the valleys?
Yeah, we could try to do something like that. I was thinking that we could try to make the mountain more not as regular. This looks like a massive.
Yeah. So constrain it a bit. Yeah.
Yeah. So, and the way we can do it is actually very simple. Is if you take this f minus 0.3 and put a parenthesis around that.
Okay.
And I can type something here.
Yeah, you can.
I need a multiplication sign though.
No.
That's my Achilles heel. Is that what you say?
Yeah, it is. Exactly what we say, yes.
Yeah. And a plus sign. That's my second Achilles heel.
You've got 2.
So multiplication sign. I'm going to P dot. What I wanted to achieve here, right, was that maybe if I multiply this by something nice. A multiplication sign again. It's a little bit. I was expecting to. Here we see
Ooh,
something.
yes. So it's starting getting
Yes.
some kind of low-lying land and then rising up to the mountain.
Low
Yeah.
line. And let's not make it go completely to 0, but we change 0.3 to 0.7.
Oh yes.
We can increase the period a little bit more. So what we did here, right, was something very simple. We just took the p.y here. Yeah, we shouldn't do it like this though. We should take the original p. So I'm gonna save this thing here.
Okay.
That's the reason I had to multiply it so many times. I get now I get it. Vec 3 OP equals p. No, it's Vec 2. The reason I had to multiply by like this much was because it's been multiplied so many times, I think. So if we take this OP now, no?
Okay.
And if we multiply this by 10, so take 10 multiplied by 10. Yeah, no, that got weird.
Got weird quick, didn't it?
Yeah. But here we see it looks like the valleys and and the only thing we sort of did here was we multiplied all these things by a global sine function that's sort of modifies the height by some and that also I think adds a little bit to the realism, because we don't expect the mountains to be as uniform kind of, I think.
That's right. Yeah, so the varying heights now.
Yeah. So okay, shall we do something with the snow as we discussed?
That'd be good.
Yeah. So then we go back to the color function.
Let's save what we got so far. Okay. Get color.
Yeah. So we have a color. We have the sand color here. So instead, if you introduce maybe a variable called surface color or something like that. So you have the sand color. That's good, but we add the surface color, right? Which is the color of the surface that we are going to do. So because snow is white and sand is not white. No, Vec 0. Yeah, Vec 0. So, and then you type, instead of sand color, you type surface color at line 101. And that's black, that's expected. And then we say, so here, surface color equal, you type it out, sand color. So a very simple way to add snow to this that will not look very good, but very simple way is to just make a height, like because we expect the top.
Top to be snow.
Yeah. So what you do is then if and the height is just the position p. So we take if p y is higher than 1, for example. I don't know exactly. We go on the experiment.
Find out,
yeah. Then surface color is equal to 1, which is snow. Okay, let's change to 0 then. Py is greater than 0.
Oh, sorry.
No, not there. Line 103. Okay, so it wasn't 0. It should be something else. 0.5. Yeah. So this is an idea, right?
Yeah.
But it doesn't look. There are many problems here, but it doesn't look, because we don't expect, right, the snow line to be this
perfect.
This perfect, right? So how can we fix that? How can we make that different? Well, so if the surface is what should I say? If that is sort of very steep, we don't expect snow to cling as easily to that. And if the surface is very flat, it's easy for snow to stick on that, right?
Absolutely, yeah.
Yeah. So that should mean, in my opinion, that we can adjust this height depending on how flat the surface is. And how can we find out how flat the surface is? Well,
the normal, is it?
We take the normal, and we multiply the normal by the up vector, and so you can create some kind of float flatness. Let's call it like that, float flatness. And take the dot product between the normal and the up vector, which is vec 3, 0, 1, 0. And if you want to optimize this, but I think this is slightly more clear what we intend to do here, because this is just the normal.y, how it works, right?
Yeah.
But I think it's slightly clear what we intend to do, and you need now the parentheses.
So I do, yeah.
So what you can do now is if flatness is 1, we want to lower the snow layer. So what we can do is we just subtract 0.6 by 0.1 times minus here. Yeah, I'm just randomizing now. 0.1 0.1 times flatness. Did that give the...
Kind of had that effect. There is a bit of an effect going on, I can see, but
yeah,
so it's kind of starting to spill over the. I think we need to
0.7 there, perhaps.
Yeah, we need to make it.
Yeah, but we can. But we saw an effect. It's not as bad as it was, right? So what we can do is we can make this more extreme than what it is. Can I try something?
Yeah, sure. Oh, yes, we're starting to get different shapes, and so that's starting to look a lot better.
So one way to make it more, the power function is very useful. Okay, and I also want to make just to be sure it's not negative. I don't think it's negative, but just make sure it's not negative. So, because the power function is a very useful function, because we can like I said, we can think about how it should be, but we can just use the power function to sort of experiment a little bit here, because power allows us to put in comma 2.0.
We can definitely see it starting to form there, can't we?
Yeah. Can you pause when we see a kind of nice snow range coming? Yeah, here. It looks better, I think.
Yeah, absolutely, yeah.
Yeah, and what we also can do is we can sort of make we can also, so this changes kind of the height, because the power function, when we multiply by, when we take power by 5, what we tend to do is all values that are not 1 get pushed towards 0.
Right, yeah.
So they become more, it sort of makes them more extreme. So if we could also go the other way around, where so it's that, but it's probably better if you go this way.
Yeah.
So
some nice effects there. So it's just here. There's some nice shapes forming in the snow.
Yeah, we can see here what.
Maybe we should try lowering take the 0.7. Oh yeah, yes. Let's try taking the 0.7 to 0.6 again, so we get some lower snow.
But this is interesting, because now we can see it's kind of forms snow.
Yeah, it's on the right. Yeah, it's sticking to the upper slopes, as you say.
So once again, it's like the math we're applying here is like super simple, and we get results that are, we have to optimize thing and sort of, it's not good enough, but we can sort of see that we can sort of maybe experiment with this thing and sort of make it look realistic. Another thing we can do is we can also make a global adjustment on the height of the snow.
It is cool, isn't it, Dragon Eye? I agree. What do you want there?
The plus sign.
Equals.
Plus
sign.
Yeah. And multiply as usual by the sine function, because we can apply kind of a sine wave to this thing here, and how should it be? Yeah, just take px plus pz and see what happens.
Oh yes.
So what happens in this thing now is now we also added kind of a global adjustment to the snow level. So it's different on different parts of the mountain range, and that also adds some kind of feeling of that is not completely, that is like, because the snow ranges get high at some point is higher and some point is lower. So that makes kind of, in my opinion, when I look at this, it looks more.
No, it's definitely, you can see that where it's flatter, the snow is sticking, as you say.
Yeah. So it
That's
makes
really good.
Yeah, but considering how little effort we put into this.
Yeah.
We computed the flatness, and we took flatness power by 7 minus something here, and then we added the global sine function to everything, and we got something that you can see. It's a start, and we can certainly improve this thing even further. But we got something, right?
Yeah, absolutely. It's amazing.
And so. Yeah,
it's the lack of uniformity, Dragon. You're right, because when things are regular, your eye naturally says that's artificial or wrong, doesn't it? But this is looking very very natural.
Let's see if we can do something with the sun direction.
Having the sun visible is quite fun.
Yeah. So what we want to do also is this thing that we want. This is something that when we talk about this, the sun looks too gray and the snow looks too gray, right?
Yeah.
Yeah. This is something we can fix by adding specular lighting to this thing here, because the sun is reflective. It's not just diffuse.
Yeah.
Because what we have here is just diffuse lighting. We don't have any.
That sounds great. Yeah.
So in order to sort of fix that part, what we can do is add specular part of lighting. But then, of course, what we should do is making sure that the rock doesn't reflect the sun
as much,
equally, right? So we need a variable here as well to sort of handle how much of it should be reflective. So let's do that.
This is so cool.
Yeah, it looks pretty good actually. I'm looking on this.
It's really, really good.
And how many lines of code do we have? 235.
But there's 2 height functions in there, I think, at the moment, so we could lose another.
Yeah, well, we could make this more, make this better. But it's okay.
Okay, so how do we do the specular lighting?
Yeah. So if you go into the get color function.
Okay.
So in order to do it, we need to compute reflect. We can stop because otherwise I'm just going to get confused. We need to sort of reflect the ray. So we have the normal.
Yeah.
And now we're going to do the reflection.
You call it specular, yeah. Okay.
So we need to compute the reflection ray, and then take back 3 ref. I don't know what's ref. Yeah, that's okay. Yes. Reflect, and then you take the normal and the RD, which is the and it might be that one of these are minus. I never remember.
We'll find out in a minute.
You find out. And then what you do is that we make it simple for ourselves. So you just sample, you just take vec3, ref sky color, reflected sky color, equal. You get good use with sky color function.
Yeah.
Get sky color, or sky color is called, yes. And you put in the ref ray here. So now what we do, we compute the reflected ray, and then we look in the reflected ray, what is how much is the
how much it contains the sky color, basically,
yeah.
isn't it? Yeah.
And then you take it's not called with you, it's just you have to remove that part.
Sorry, where?
It's wrongly named.
Okay, it's got this for you. I can't spell the American way. Well, I can't spell, but you know.
If I knew, you know, I don't have any, you know, I'm not English or American. I don't have a strong opinion on this thing. Well, we can just see how does the sky color look if you just take col equal ref sky color. See how that looks. It's gonna look weird, but
yeah, like an acid dream.
So let's try to get this neg. Oh, didn't do any difference?
Don't think so.
That's weird. What I'm trying to figure out is what we're looking at is
negative, yeah.
This looks better.
Looking better.
Right? This looks more like it should look.
Mm.
I think so, right?
Yeah,
because
definitely,
now
yeah.
Yeah. So okay. I actually live in Norway as well, Dragon Eye, but I live in Oslo, so it's not really that north.
You're in North Norway, Dragon. I didn't realise that. There's lots of Scandinavian viewers. It's very interesting.
So now I have the surface color. So how do you do this thing here? Well, so what I'm thinking is that grad. One simple way of doing it is just doing it like this. But it's going to look wrong because it's not going to take the shadows into consideration.
What do you want there?
Sign?
Plus almost. Plus.
Yeah. Yeah, but that's probably ref sky color. So let's get 2 instance, but then we multiply this by 0.1, something like that. If you can design, and then we also multiply this by shadow. So it actually takes shadow. If it's in shadow, we don't shade. It's not shadow.
Shadow, isn't it now? Yeah.
That's why does that look weird?
Is it? This shadow, yeah.
Let me see. Because it got too intense again, right?
Yeah.
Is shadow negative sometimes? It becomes more intense because this added brightness to it.
Yes.
Okay, but let's experiment a little bit more. Multiply by that. So
So it's starting to get the effect.
Yeah.
You can see,
So,
the reflected lights is
so,
there.
so
But
yeah. So what we do, we need kind of float ref factor here, perhaps. I'm just 0, perhaps.
Mhm.
And then what we do is we say ref factor equals 0.3 here. Factor.
So this is taking the material of the surface.
But don't you think this improves it a little bit?
That's definitely improved, yes.
Because now the snow isn't as dull as before.
Yeah. So we fly over it to have a look, and you can see you can see some reflection. Yes, that's much better.
Yeah. We see the highlight there, right?
Yeah.
So I think this improved it quite much, actually.
Yeah, a lot.
The snow is now much more white, and it also have this. More intense colors, right?
Yeah.
So you can change this to 0.5. See what I think that's going to be too much, but let's see what happens.
I like it. No, that's nice.
That was good, actually.
Just means the sun's a bit brighter.
Huh. I mean, this is not bad for a few hours of gambling, right?
Absolutely. That effect is really nice now. The sun's sparkling off the snow. But you also get some variation on the ground as well, as you say, just less intense, which is really nice.
Yeah. So I'm going to introduce another trick now to make this, I think, look even better. Right? Because we want better.
Yeah, we want more. Dragon Eye wants more.
Yeah, he wants more. So how are we going to do this thing here? So what I want to do is I want to increase.
Oh yes,
Because I want to increase the sort of the details in the mountain.
Yeah.
I think the snow looks fine with the details it has, but the mountain range looks a little bit more. I want more intense details in it.
Mm-hmm.
And the way we get it is to improve the normal. And why don't we get the more precise normal? Well, that's because we don't iterate more times.
Okay.
But the thing is, now we're going to do a trick here. We are not going to gain the mountain range itself is not going to change so much. So we're not going to gain fidelity by increasing the count that much. So we're going to just lose a lot of clock cycles. But what I'm going to do instead is we're going to use different height functions to compute the height when we're ray marching and to compute the normal.
Okay.
Because then we get a higher level of degree in the normal. And then the mountain will look more detailed and more details. Like it looks like now it looks kind of dull. I don't know if you agree.
Yeah, there's a definite dullness. It's a misty day, certainly.
Yeah. So let's see if that goes out. Let's save this thing though. We've done a good job so far.
Okay, saved.
Yeah. Maybe this is Kobe's alpha planet we're working on.
Yes, it could well be Alf's planet. Yeah.
So this is just now because we are a little bit performance hungry. We are also not going to do. What we're going to do is, and we also don't have access to cool things like virtual methods and all that kind of thing. We have to do a little bit of code application, but we do that for the good, right? We are doing.
Yeah.
So I'm going to do. Can you copy paste?
Have you copied?
Copy paste.
There you go.
So I'm going to call it a high precision, and then I'm going to change the loop count here. This is the only difference to 11. Now I'm going to use the high function here, when we are computing the normal. Let's pause it. So here is where we were. Now we have more details, I think.
Yeah, it's starting to pop, isn't it?
But there's not much difference between 12. At least on my screen, I don't see much difference.
Doesn't seem a lot of difference between 11 and 12, no.
So try to find a good one from your perspective. That where the more we add, we don't get any more precision. No,
I just want to move a bit closer to something that's where we can see it. So.
Okay. Because I can't tell the difference on my screen. Because we want to keep the numbers as low as possible in order to make it right, to not take too much CPU time or GPU time. But we want to keep it as high as possible to get the maximum precision out of it.
11 seems okay.
Let me take 11. I just guessed 11. Okay, so that's cool. But the problem now with this thing is that the snow now looks, I think, worse because it has too much details. We kind of want to have less detailed on the snow because the snow makes the snow, adds a layer.
It's smooth, isn't it? Yeah.
Smoother it is, right? So in order to do that, we actually have. I'm going to suggest we make a normal high, like this. Copy paste this thing. And then we have two different normal functions. One for one that we compute for the where did I go? No.
Looks okay.
No, yeah.
There. Yes, and missing up there.
So because then we use what I want to do now is depending on if it's snow or if it's mountain, we're going to use different normals.
Oh, okay, right.
So let's. So here I copy paste this line.
Oops. There we go.
And then we go, this is a high normal. So this is the high definition normal, right?
Yeah.
This is kind of low definition normal. And what we're going to do then is we take this part where we have the surface color down to this line here and move that above and move that above the diffuse lighting if it's possible. So line 206 to line 214.
And under specular lighting, yeah? Under diffuse lighting.
No, over specular lighting, if it's possible.
Okay.
That worked? Okay, cool. So then it's very simple here. The only thing we do now is we say normal, if I can type. I mock you for not being able to type.
It's catching.
I mock you for not being, and then you type normal high. That's the wrong direction. I realized. Okay,
normal high equals, yeah.
Or then you type else rather. Remove here, and you type else.
Down here.
Yeah. Now we are hitting the mountain. And then you type normal equal normal high. So what I'm hoping to see is that we actually now have more details on the. Can you tell that? Yeah, I think so, right?
I think so.
Exec. Can you also take the slope of interangling count with snow? We do that actually. So because if you don't, it would be very, very uniform and sort of a very sharp line.
Yeah, so we calculate the flatness here. You can see exec. So we get the flatness of the surface, and so the snow sticks to the flat surfaces. This is why we get these breaks where we have a steep surface here. It's not sticking. It's all through a bit of linear algebra. It's
yeah,
not
exactly
assumption.
right. See, because this is that part of the surface is steeper that has no snow. Can you, if you go over to where we have more mountain range and less snow? So if you go forward a little bit and stop here, and then you comment out line 204.
There's a change.
Yeah, but we have a better normal here. It's not maybe so intense, but it's something, right?
Yeah, it's definitely a difference. It's more blurred.
Yeah.
Without that, yeah.
And this could also allow us to make the snow even more smooth, because we could reduce the precision even further by making a low. We have a high definition normal. We can make a low definition normal, kind of, that uses a height function low, and then reduce the precision, reduce the normal even further to make it even smoother if you want to.
Let's give it a go and see what happens.
Sure. And then of course you have to make a normal low version.
Yeah.
Get normal low. It uses and that should then use the height function low in every place. And then you change the number of iterations in the low version to maybe a bit fewer steps, like say 4. Okay, that's cool. And then what you do now is when you compute the normal, you can I change the code? I change the code.
All yours.
Go low. Hello, can you go? Is that the song? Rec 3, no.
We fly a bit forward.
Yeah. I think we lost something here.
We lost some of that, yeah. So
yeah, pause it.
Yeah.
I think we lost something else. There's something else that doesn't match here.
Yeah.
No. So here's the thing.
Yeah, the flatness. Yeah.
Yeah. Okay. I get it. I'm not sure this is such a good idea, but let's. Why not compute all the normals?
We need to lose this line as well. 223.
Yeah. Yeah, lose that line.
There we are.
Yeah. So now it's too low. We can certainly see.
It's like the
we see that, but then we go up to this function called the height function, and then we try to find something we're happy with, and we probably end up with 7. I'm just predicting that's what's going to happen. Yeah, maybe 7 is the right number.
Yeah, could well be. Yeah.
But you see, the point is not really perhaps that we are using a low number. The point is that we can find all these kind of ways to sort of create effects that it looks smooth by cheating with the normal, having a less precision normal, and having a higher definition normal to sort of get effects that look more detailed.
Yeah.
So that is the key takeaway here.
Yeah, Dragon, I've learnt my lesson. We're saving virtually all the time, though.
Let's run this thing and see how it looks now when it's scrolling through the landscape.
With this, yeah. I certainly like the sparkling on the snow now. That's really, really nice.
Yeah, I mean that's really improved fidelity, because before it was very dull, right?
Yeah.
And it looked like it didn't look like snow should look. So I'm thinking it's getting kind of late here.
Yeah.
But
been going for 2 hours and 40 minutes now.
But I also think we can be quite happy with the result.
Yeah,
don't
absolutely.
You think? So we can certainly continue next time if you want to.
Yeah, I think I think there's more we can do to this. It'd be really nice
we can add vegetation, and we can add clouds or fog. That looks very nice.
Maybe a bit of water at the lowest levels.
And water as well. It's very easy adding a water layer, but then we need to add the normal to get the water to look nice, but it's no problem adding a water layer. That's very simple to do. So I think the many things we can do here. Well, we could try to make the water, actually. Shall we try to make the water before we stop?
Water would be nice, wouldn't it?
Yeah.
Water at different levels, you think? Exizek, yeah, it's like tarns and things like that. Yeah, but let's get water in to pool in the lowest areas first, shall we?
Yeah. So you stop the iteration. Yeah. So we're going to start primitively, but we sort of just show. So we do it similar to how we do it with the
snow.
With snow, yes.
So into watercolor, I suppose, do we?
Now I'm thinking.
Okay.
So if I have the water, I think you add this as an if here. Add an if here around everything.
Here, and those.
So I need to think a bit here. Because water needs kind of special handling.
Okay.
No, it doesn't need special handling, or does it? Yeah, it does. See, let me think, because we don't need all this stuff here. We don't need to compute the normal. Now, with shaders, it's not as simple that we don't need. So what I'm going to say here.
Yeah, because it computes both. It goes through both branches of the if statement, doesn't it?
Yeah,
it's the problem with the ifs. Yeah.
Yeah, it can certainly do that. Now, if you have a cluster of what they call wavefronts that don't do that, then you don't pay the price. But it can certainly execute through both branches. That happens.
Mm-hmm.
So you don't want branching, but I think in this case it makes sense. So add the brackets. And else. Okay, I control now.
Yep.
And put. Let me see here. Yeah, here it should be here, right? Yeah. Here is the end bracket, right? What is it complaining about? Oh yeah, if false, just say false. So that works.
Yep.
So if p.y is less than
So I'll do that for you.
less than 0. Okay, nothing happened.
Oop, okay, there's possible water area.
Okay.
Ooh, that looks nice.
Yeah, I mean, it's very, very primitive. But this allows us to sort of say, well, you know, let's compute for the fun of it. Let's just compute the reflection here. So the water normal, the normal at this point.
Okay, I'll stop here.
Yeah.
Sorry, we're tripping over each other.
WEC3 normal. That is just pointing right up. WEC3 0 1 0. And then you copy paste this reflection code you did before, where we compute the specular lighting. And let's just return the ref sky color and see what happens. It's gonna look weird, but let's see what happens.
I don't know, that's almost it, isn't it?
Yeah, it's too intense.
Yeah.
It's multiply by 0.5 or something like that. Okay, it's something. Let's also bring in the shadows. So let's compute the shadow here. So here the position P, what is the position P here, right? It's not, now you need to have the sun deer. So the sun deer you can move up. You computed sun deer, so you can move that out here. So yeah. So the position P here is not the correct position. The position P is where we hit the position P is where we hit the mountain, but now we hit the water surface. So we want to find the position P where the ray intersected the water. And this is not very hard to compute. It's just that I'm a little bit too lazy to compute it right now. So I'm just going to find how I've done it before, and then we can compute it. Like I said, it's not very difficult. It's just a linear equation system, but there are a little bit, a few things to keep in mind.
So, Dragon Eye, Ice on the Sea, we'll leave that as an exercise for the viewer.
Yeah. That should be easy, right? Should be easy. Let's see now. PSC, DC.
It looks great as it is. I think it's really starting to. I mean, it's obviously. Well, I've just flown over the water, so let's hopefully we find some.
Yeah, but the water looks like something.
It does look like
right?
something, yeah.
Yeah, so we can certainly improve it. Here I found something, a little bit of code that I've written before. Now we just need to share it with you somehow.
Yeah, okay, chat.
Yeah, and the problem is I found it on my other machine because I have a laptop, and that laptop is just.
Oh, right.
it can't handle this stuff. It's just too hard for it. So I have to use my.
You could use chat if you want.
Oh yeah, I could do that. That's a good point.
Team chat, that is, rather than Twitch chat.
There you go. So put that above that code under Sundeer. If you see in chat.
Oh, I see. You did put it in chat. Okay.
It's a little bit more advanced version of what we're doing. Ambient, I think you can probably drop. That is not that ignore that ambient thing that you don't need, but you need if thing after it, and use that if thing to replace the if you have. So what this is lacking is a C height, so then you define a constant C height, and we set it to 0.4. Good. It looks the same, but this is a little bit more stable computation. But the good thing is now we have the DC. We have the distance to the C.
Oh yes, of course, yeah.
Yeah. So now we can compute the PC, and the way you do it is you type inside a if statement.
Yeah.
You do vec3 PC equals RO plus DC times D. No, times RD, sorry. And yeah, DC, C is lower S. Now, this you should be able to put into the shadow function. So if you put PC, and then you multiply the ref sky color by the shadow value. And about 0.5 as well. So it's too intense, right? But now you see the shadows.
Yes.
So it's too intense. That's okay. So then we can type here. Yeah, but the ref colors should be covered by the shadows. But let's see now how we do this. Plus.
Oops. Plus.
I'm thinking again. Always painful.
I can hear the cogs whirring.
Yeah.
It's really nice with the sun in that position because you get the nice reflection of the sun off the water there.
Why doesn't it move? Vec3. (0.3). This is red. Oh. Yeah, I mean we are just gambling here, right?
Getting close though.
But you can see the shadows.
Shadows there nicely, yeah.
On the water, and we can improve this. So it doesn't look right. I agree, but this is a start.
Absolutely. I didn't think we'd get this far in on the stream. I must admit, to get the water in there.
Yeah. So
nice.
the way we improve the water is we getting water. We want the waves, obviously, but the water could be flat. But we want the waves. The water should also change. It has this behavior that if you look down into water, it's more dark. We see the bottom more than we see if you have a flat angle. This is what we talked about last time, the Fresnel's rule. Yeah.
Yeah.
And then of course here we should see sort of, the ground extend beyond the sea level. So there should be
a bit of transparency,
some kind of transparency going on there. However, we had nothing when we started.
No, we literally started with a brand new project, so yeah. We get little lakes forming with this. That's really quite nice.
I want to see how it looks on yours. Yeah, well, we see some reflection in the water. It could be more intense. That's fixable. How do you do that?
Well, did you want to leave that till next time? Because as you said,
I think we should leave. I'm sitting here just thinking about things I want to optimize.
Yeah.
But I should stop here, right? I think we can be quite happy with what we've done.
I think
right?
Absolutely, yeah, it's great.
This is a real-time ray tracer.
That's what I keep having to remind myself. This is all happening in real time. It's not...
and we have no assets. Everything is kind of generated, except the noise. But the noise is also generated by math. So we haven't really added any like textures or anything. We just everything is just computed using mathematical functions.
Yeah.
And we still get a decent result. We can improve it a lot. But I think we've done pretty good for one night.
I think so. Right, I'm going to what I'm going to do is upload this to GitHub so that the viewers can try it out for themselves. So
yeah, and you remember I demonstrated my Magnum Opus last time.
Yeah.
This is how I started, obviously.
Yeah, absolutely.
Yeah, so I was very happy when I got to this point, and then of course you think, okay, what is the next step? How do we improve from here?
And just keep on going.
Yeah, and we can add this banding. Well, I don't know what it's called, but the mountain has like light and dark areas.
It's like the strata, isn't it?
Yeah. That is quite simple to add as well, actually. So many of these things that are quite simple. Of course, it means that they're just pure cheating, but that's what we do here.
Well, I think it looks marvelous. Really do.
I think the snow,
the snow's fantastic. It really is, yeah.
The water I want to improve, but the snow I think is. Do you see the sun reflection in it? It's actually pretty appealing.
So the other bit which is slightly odd is the shadows still look a bit weird, but you just need some light to spill across, doesn't it?
But I think we can pat ourselves on the back for the snow.
Absolutely, the snow's really good.
Job there. And there are room for improvements.
I think we started off with a sine wave.
Yeah, exactly right.
Thank you very much, Dragoneye. I'm glad you enjoyed the stream. It always amazes me how we end up with something that's of this kind of quality, which is just for a few hours work. And obviously, people when they're doing the really nice shaders on Shader Toy, spending an awful lot longer than a couple of hours over it.
Yeah, but so I talked about that before. What I hope we can get across when doing these streams is also that now if you look at some mountain range at Shader Toy, and you can appreciate, of course, the amount of effort this guy put into making it work. But I hope that you get the feeling as well, thinking, I kind of know how they do it.
Yeah.
It's
no longer magic, is it? It is accessible, even if they use some functions and some techniques that you don't particularly grasp what they're doing. You know that they're just manipulating the various parameters.
Oh, look at this. This is interesting. Half island there.
Yeah.
Back here. Did you see something here?
This must have taken out into the sea, the little star-shaped island. It's fantastic just to kind of just sit there and watch it. Actually, what's coming up.
Yeah. So here you can put your little airplane base.
Yep.
Cobas Alpha. You launch the rockets from here.
Yeah. It's a bit like that, isn't it?
Yeah. So at time 4:36. No. Yes. But I also think So, and if you remember I showed you this terrain shader I made.
Yeah.
So the way I did is, I had like different sort of views of how it worked, but I was just mainly manipulating. So if you remember, there is a part of it when you see a single mountain standing out of the water. How is that working? Well, that is the same thing, but I just apply a different global function. So that means that everything that is close to the center of the mountain is multiplied by 1, and then it falls off to the edges.
Right, yeah.
Yeah, so then I get a mountain. And so it's just manipulating this global kind of function, because the thing that drives here, these valleys and things, that's just a sine wave.
Yeah.
That comes back and forth.
I think it was XYZ who was saying, talking about the flatness. We'd already done it, but it's amazing that that we can think in terms of, snow gathers on flat surfaces and falls off steep surfaces.
Yes.
There's actually we can translate that into a very simple mathematical concept of the normal.
Yes. And when you see games, I think it's easier to understand games when you see how do they do the mountains. They probably do the same thing. They blend different textures depending on the normal. So like here we're like, so many things becomes, you remove the magic of
you mystify them a bit. Yeah.
Of course they put in a lot of effort, but you kind of grasp the core concepts, I think.
I think so.
Very good.
Great.
I think we've done good here.
Yeah. So that's all up on GitHub. So if you want to check out that code, it's a Kodelife file.
XYZ, this tool we're using here, if you weren't here from the beginning of the stream, we're using Kodelife. So if you want to open this project, which is KPro, you need a Kodelife tool. But it's free and downloadable from this hexler.net. Yeah, you posted that.
I just posted that. So just download Kodelife from there, and you'll be able to open these files. And
I think it's for Windows, Mac, and Linux.
Yeah, it's cross-platform certainly. So you can. There's no impediment if you're using you're not using Windows machine like we are. Well, I am. Yeah, and I'll put this up on ShaderToy as well when I get a chance to convert the code over to ShaderToy. We'll have this as another one on there.
Of course, that I think is a very good idea to do, because it's, the Kodelife is great, but I think ShaderToy is great to share your shaders with, and also it's good for others. I mean, even if this is a simple, I think what I think is great to have on ShaderToy is both very nice looking, complex, and also something that is you can understand,
more accessible. Yeah.
So I think it's very good to put it up. I put up things on ShaderToy which was not like that amazing, but I thought, it's a little bit cool. Very good, I think.
Fantastic. Okay, so thank you very much, Mårten. That's another wonderful stream. So I really do appreciate the effort you put in and the work you put in behind the scenes to get this to get us to this stage. It's fantastic. Okay, so next stream will probably be on Wednesday. It may be a little bit later than normal, but it's probably going to be in the afternoon UK time. So we'll either do some work on the text adventure, or if I'm feeling up to it, my new project is an emulator for the Z80 chip that used to power computers back in the day. I think things like the ZX Spectrum. I think even the Game Boy used to use a variant of the Z80. But we're not at this stage wanting to emulate game consoles. It's really just an exercise to emulate the chip itself. That's a new project I started working on yesterday and did a bit more work on today. Very, very early stages. There's an awful lot of work to do, not all of which is going to be interest to the stream. But what I'm trying to do is take a test-driven development approach to that, so that we've got good test coverage for the various operations that you can do on the chip. So that's a second CPU in your BBC. Now, were they 6502s originally? The BBC micros? Can't remember because I used to program the 6502 way back because my very first personal computer, hobby computer as it was called then, was a 6502 based system. So I did that. But the reason why I started to get interested in this chip emulation was that there's a guy called Javid X9 who is currently doing a series of YouTube videos on emulating the Nintendo Entertainment System, which is a 6502 based early game console. And I just thought what he was doing was fantastic, and just decided, well, I'll do something similar. I'll do it in C#, and I'll do the Z80. And yeah, the kind of ultimately, I'd like to get CPM operating system running on my emulation, but whether we get that far is another matter. But I may introduce that to the stream at some point, maybe on Wednesday, but more likely to be Text Adventure on Wednesday. Okay, so this video will be up on YouTube within 24 hours. I have to wait 24 hours because of my affiliate agreement. Twitch get the video for 24 hours exclusively, but my YouTube channel is over here. So please go and visit. If you're not a subscriber, it's free to subscribe. Hit that subscribe button over on YouTube. If you would like to follow me on Twitter, here's my Twitter account. So go and follow me on Twitter. Once again, that's completely free to do so. If you're not a follower of the stream and you happen to be in chat, then please do hit the follow button. We're trying to get to 300 followers. Currently at 271, so we're kind of getting there. And so hopefully, Mårten, you'll be able to join us next Monday for another shader stream where we kind of take this forward a bit.
I think I will be able.
Excellent. If not, it's not a problem, but we'll just need to kind of plan.
No problem. I just need to check my calendar.
Yeah, that's okay. So we'll just discuss that over Discord and make sure we can arrange a suitable time when it's convenient to yourself, because I know you put an awful lot of work on, on preparing for this, and you are on call a lot of the time as well, aren't you? So you're on call today?
No, actually not. This is first.
Excellent, because normally when you're on call, aren't you?
Yeah, I'm just waiting for the phone to call.
Yeah.
But to be honest, yeah, it's a little bit of preparation. But I just look at my old samples, things I've created, and just trim it down. So it's not too bad. Then I get a little bit embarrassed when I have to think too much on a stream. I hope that's okay.
Oh, it's absolutely fine. A lot of the times I get completely stumped, and there's a couple of times I've had to end streams because I couldn't solve the problem. And the minute you close the stream, you solve the problem. Literally, the minute you close the stream. Okay, I'm going to let you get on there, Mårten. Thank you so much for joining us. And I'm going to. I don't think there'll be anyone to raid. We'll go and see if there is anyone to raid. We'll go over to Twitch and see if there's anyone around. But it's a bit late. Who have we got over here? We've got Source Scoot. Looks like he's on. We'll go and raid Source Scoot, I think. So he might be doing Ludum Dare. I'm not quite sure what he's doing at the moment. Let's go and see. He's working on a game of some kind, so let's go and see him. Source Scoot. There we go. Okay, so we'll raid Source Scoot. Do stay in the channel if you want to go and see his stream. Otherwise, I'll see you again very soon. Wednesday, the most likely time. So thank you everyone, and good night to you all.